Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 3.2 from your textbook, which was our investigation into the properties of determinants. To start off with, I'd like to quickly review one of the sort of major theorems that we discussed in the previous video, and then look at a quick example that sort of relates to it, especially when discussing solution sets of systems of equations, which, if you sort of remember back from chapter 2, is really what sort of started our whole investigation into matrices. So, remember from last lecture that we had this sort of crucial theorem here, which said that if you have a square n by n matrix, then that matrix is invertible if and only if the determinant is non-zero. Keep in mind that this was an if and only if statement. We actually proved this in the previous video. Because it was an if and only if statement, this actually gave us four different sort of ways of sort of reading this. It tells us that if A is invertible, then its determinant is non-zero. It tells us that if the determinant is non-zero, then the matrix is invertible. It tells us that if the matrix is not invertible, then its determinant is guaranteed to be zero. And it tells us that if the determinant of a matrix is zero, then it is guaranteed not to be invertible. Keep in mind that also, back at the end of chapter 2, we established the invertible matrix theorem, which was just a bunch of equivalencies for what being invertible meant. Remember, being invertible means that the matrix has an inverse, so in other words, A inverse exists. Remember that it also means that the rank of the matrix is full, so the rank would equal n in this situation. It also means that the matrix is row equivalent to the identity matrix. Now we can say that an additional equivalency, so if we wanted to rewrite the invertible matrix theorem, we could include determinant of A non-zero. So at the start of this video, what I'd like to do is just take a look at a sort of example that talks about this sort of theorem in regards to solution sets to systems of equations. So we're going to take a look at this example here, and this example should seem pretty familiar. We did one similar to this when we first began our investigation into systems of linear equations and how matrices and rank sort of tells us about the solution set. We're just revisiting that now that we understand these concepts of invertibility and determinant. So what we'd like to do in this example is for each of these, we're going to try to describe the solution set as fully as possible, and we're going to, again, assume that whenever we see a b in one of these, that b is not equal to 0. Of course, there could be the situation that there might be several cases or something like that, so we'll have to go ahead and break it down into several cases if necessary. So let's take a look at A here. So we have AX equals B. So this is a non-homogeneous system. A is 5 by 5. So we have 5 equations and 5 variables. And we know that the determinant of A is equal to 6. So the first thing that we should tell here is that the determinant of A is equal to 6, which is non-zero. So this implies that A is invertible. Now, when A is invertible, we prove that another equivalency to A being invertible is that this type of system always has a unique solution. So we immediately know that this will have unique solution. Can we say what that unique solution looks like? Well, we don't actually have the values or anything, but we can describe that unique solution a little bit. It's x equals A inverse B, because we know that it's invertible, so we could apply the inverse on both sides and get x equals A inverse B. So in this situation, if we had a 5 by 5 system where the determinant of the coefficient matrix was 6, we automatically know that it's an invertible matrix. So we know that there will be a unique solution, and that unique solution will have form the inverse times the original system constants. Okay, now we have AX equals 0, where A is 7 by 7. So we have 7 equations and 7 unknowns, and the determinant of A is equal to 0. So the first thing we can tell is that the determinant of A is equal to 0, which implies that A is not invertible. Now, unfortunately, being not invertible just simply means that it does not have an inverse. So we definitely know we're not going to get away with something where we can just say it's A inverse or something. So what does it mean to be non-invertible here? Well, this tells us that the rank of A cannot be full. It cannot have a full rank because A is non-invertible. So we now know that the rank of A is less than 7. Now, normally, we'd have to break this down into several cases because there's the chance that the rank of A augmented might not be 7 and we might have no solutions. But keep in mind, this is a homogeneous system. AX equals 0 implies this is the homogeneous system. Remember, homogeneous systems always have solutions, so this implies that it's consistent. So we know that it's consistent, and we know that the rank is going to be less than 7, so there's no chance that it's going to be inconsistent, no solutions. So in other words, we know that this thing will have infinite solutions with 7 minus the rank of A free parameters. How do we know that? Well, the way we determine the number of free parameters is always the original number of variables minus the rank, and we know that the rank is less than 7. We don't know exactly what it is. Because the determinant is 0, the rank could be 6, 5, 4, 3, 2, whatever, right? So we know we're going to have infinite solutions with 7 minus the rank of A free parameters. That's the best we can say there. All right, let's look at C here. So we have AX equals B, where A is 4 by 4, so 4 equations and 4 unknowns, and the determinant of A is equal to 0. So similar to the last one, we can say that the determinant of A is equal to 0 implies A is not invertible, which tells us in this case that the rank of A must be less than 4. Okay, now, is there the potential for this system to be inconsistent? Well, the rank of A is less than 4, and certainly we can see that A augmented is going to be 4 by 5. Right, it's going to have an additional column. That means that the rank of A augmented is capped by that 4, which means that the rank of A augmented might be as high as 4. Rank of A is less than 4, so it's 3, 2, 1, 0, something like that. That means that the rank of A augmented could be larger. So we're going to have two cases. So we would have case 1, rank of A augmented greater than rank of A, or we could say rank of A augmented equal to rank A plus 1, since we established that the rank of A augmented is always the same or 1 higher. But we can just say rank of A augmented greater than rank of A. That imply no solutions or inconsistent. And then case 2 is, of course, that the rank of A augmented equals rank of A, which is going to imply, well, since the rank of A is less than 4, we're going to have infinite solutions again. So infinite solutions with, well, we had 4 variables originally, so it's going to be with 4 minus the rank of A free parameters. So in this situation, because this is a non-homogeneous system, there is the potential for no solutions. If there are going to be solutions, since it is non-invertible, the rank is less than 4, which guarantees that there will be infinite solutions. So there's only 2 possibilities here, either no solutions or infinite solutions. Finally, we have AX equals 0, where A is 6 by 6, and the determinant of A is negative 1. Notice we don't really care what the value of the determinant is. We just care if it's 0 or non-zero. So it doesn't matter if it's 6 or negative 1 or pi squared minus e to the 7th. All we care about is that the determinant is non-zero here. So we can see that the determinant of A is equal to minus 1, which is not equal to 0, which implies A is invertible. So since A is invertible, it's going to be just like this here. We know that there's going to be a unique solution. So we can say that there's going to be a unique solution. What is that unique solution going to look like? Well, we could say x is going to be A inverse 0, but we actually can say a little bit more. Whenever you have a homogeneous system and you have a unique solution, we know that that unique solution has to be x equals 0. Because remember, homogeneous systems always have the 0 vector as one of their solutions. So in this case, since we know it's a unique solution, we know that the only one is x equals 0. Okay, so this was just a quick example looking at solution sets to different systems where we knew some information instead of about the rank of the matrix, about the determinant of the matrix. Now, one thing that I would like to call your attention to, especially if you decide to go back to the Chapter 2 video where we did an example similar to this, is make sure that you understand that since we're talking about the determinant here, these matrices all had to be square matrices. Each of these was 5 by 5, 7 by 7, 4 by 4, 6 by 6. That's a necessary constraint because if you had a non-square matrix, you wouldn't be able to talk about things like the determinant or invertibility. Those concepts, they just don't apply to non-square matrices. We understood how to analyze solution sets for non-square matrices. There we would have to be given information about the rank. Just be aware that our sort of analysis here, it's related to that rank analysis, but it's a little bit more detailed here because we have these square matrices and because we've now investigated determinants and invertibility. Just be aware, though, if you run into another situation where you have non-square matrices, you can't use the determinant or invertibility as part of your sort of discussion. Okay, so that was just a sort of quick way of sort of recapping this important theorem. The other major thing we did in the previous video is that we started to establish some properties of the determinant. So I'd like to summarize some of the ones we discussed from our last video, and I'd like to go ahead and take a look at establishing the rest of the major properties for the determinant. So this is a sort of list of the properties of the determinant. And I've tried to organize these properties in the same way your textbook does, so that when I talk about something that is property 1 of the determinant, your textbook talks about it in the same way. So we're ultimately going to go through this and talk about 10 different properties of the determinant here. Some of these we'll have already talked about. Some of these we've actually already proved. Some of these we will actually now prove right after this discussion. And some I will just leave for you to try to prove on your own. Or if you want, all the proof of every one of these is in your textbook, so you can just reference them there. Okay, so for all of these, we're going to talk about properties of the determinant. So we're going to have two matrices that are the same size that are square. So A and B are n by n matrices. So the first three properties here are all properties that we discussed in the last video, which were about the elementary row operations. We said if B is formed from A by interchanging two rows, then the determinant of B is negative the determinant of A. We actually stated this and proved this in the last lecture. Property 2 said that if B is formed from A by multiplying one row by a non-zero scalar k, then the determinant of B is k times the determinant of A. We stated and proved this in the last lecture. Property 3, which was for the last one about the elementary row operations, said if B is formed from A by adding a multiple of one row to a different row, then the determinant of B is equal to the determinant of A. Now, we stated and used this a bunch in the last video, but we haven't actually proved it. And actually, we're going to prove several other little properties just so that we can actually prove this one, because I think it's most important that you guys do see the proofs of these first three, because, like we said, we really want to understand how the elementary row operations impact the determinant. Property 4, which we actually stated as a corollary of property 2, said that if B is equal to Ka, so in other words, if matrix B is a scalar multiple of matrix A, then the determinant of B is equal to k to the n times the determinant of A. And remember the way that we proved this, and proved in quotation marks because it's a very we just gave a short verbal proof, is that if you do k times A, you multiply each of the rows of A by the scalar k. Since A is n by n, it has n rows, which means you perform this operation n times. So you get n factors of k, which is why it's k to the n. So by proving this, we just basically gave a verbal explanation of how this property here leads directly to this one here. All right, now, after that, we're going to get to a whole set of properties that we haven't really talked about yet, properties 5 through 10. So we'll talk about these, we'll discuss them a little bit, we'll prove a couple of them, and then we'll leave the other ones for you to either read in your textbook or try on your own. So first, property 5, that relates the determinant of the transpose to the determinant of the original matrix. It turns out that the determinant of the transpose is the same as the determinant of the original matrix. So this is a pretty important one. I'm just going to sort of star some of these as we go along. The reason that this one is so important is because it shows you the relation between the transpose, which again is one of these sort of really special matrix operations because it is one of the few operations that only make sense for matrices. A lot of the other stuff, right, we've sort of built them to parallel things that make sense for normal real numbers, complex numbers, scalars. But the transpose is very unique to the matrix structure. So it's always good to know how these new things work with the transpose. And in this case, the determinant of the transpose is the determinant of the original matrix. P6 is a very weird property, so I'm going to talk about it a little bit, give you guys a quick example of it, and it turns out that this is mostly an important property for proving some other properties, but we should talk about it. This says, okay, let's let row 1, R1, R2, Rn denote the rows of a matrix A. So each of these are the rows of a matrix. So then we're going to suppose that matrix B has the same rows, except in the kth row, it has B sub k, and matrix C has all the same rows, except again, in the kth row, it has C sub k. And we're going to suppose that the kth row of the original matrix is the sum of these two rows. Then the determinant of A is equal to the determinant of B plus the determinant of C. What this is basically saying is that the determinant does not distribute over addition. So in other words, the determinant of A plus B is not equal to the determinant of A plus the determinant of B. Instead, it's a little bit weirder. What it's saying is that it distributes over addition, but addition in one single row only. meaning that if you have two matrices, and if you were to sum just one of their rows, which is not how matrix addition works, but if you were just to sum one of their rows, and that would combine to the row of your matrix, then the determinant of your original matrix is equivalent to the sum of the determinants. Now again, like I said, that one is a little bit weird, so let's just give a little bit of a visual example here. So let's actually give a matrix. So imagine we had some sort of matrix. So maybe we have something like 1, 2, 1, and then maybe we have something like, we say 0, 2. Oh, you know what? Let's do it more like this. This will make it a little bit more interesting. 1, 2, 3. 4. Here, yeah. This will be a better one. 4, 0, 5, and maybe 0, 0, 1. Okay, so say you wanted to calculate the determinant of that matrix, so I'll put it into the sort of determinant form. Okay, now you could use some of the operations that we've done so far, but you notice that this thing is definitely not upper triangular, right? There's stuff down here that's non-zero, and it's not lower triangular. There's stuff that's up here. So you could play around with it. It wouldn't be too hard to say use this to go ahead and like remove the stuff here and go from there. But what this theorem is saying is that if you leave all the rows except for one untouched, so let's leave the top and the bottom sort of untouched, and let's break this row up as a sum of two different rows. So why don't we do 4, 0, 0 plus 1, 0, 0, 0, 0, 5, 0, 0, 1. Okay, you will notice that if I add this row to this row, I get this one, and everything else stayed the same. That's what this is saying. So you're only summing up in one row. In other words, this is saying that the determinant here is then the sum of these determinants. So you could then see why that might be useful, like in this weird case. This then would be lower triangular, so we could get the determinant here, since this is lower triangular, as 1 times 0 times 1. And this one would be upper triangular, so we could get the determinant there as 1 and 0 and 1. And then we could see that that's 0 plus 0, and we'd get that the determinant overall of this thing would be 0. Now, is that super useful? Well, probably not. You could just go back up here, use this to zero this out for, row 2 minus 4, row 1, and then just use the fact that then you would have it in upper triangular form. But it just shows sort of an interesting idea. If you split a single row up as an addition and leave the other rows identical, then you can say that it's the original determinant is the sum of the determinant of those. In general, though, you should just keep in mind, as sort of a note here, note, determinant of a plus b does not, in general, equal the determinant of a plus the determinant of b. So in general, you do not get to distribute determinants over matrix addition. You get to distribute them over this weird addition of a single row at a time. Okay, let's talk about some of these other properties, P7 through P10. P7 says that if A has a 0 row or 0 column, then the determinant is automatically 0. Notice that if we had P7, we could have just immediately deduced that this thing was going to have a determinant of 0. But this is a good one to remember. It's very easy computationally. If it has a 0 row or 0 column, then the determinant of A is equal to 0. You can imagine a very quick verbal proof of that. If it has a 0 row or 0 column, then it cannot be row equivalent to in. And since it can't be equivalent to in, then it can't be invertible, so the determinant must be 0. P8 says that if two rows or columns of A are scalar multiples of one another, then the determinant is automatically equal to 0. So if you ever see something where one row or one column is a multiple of another one, then you immediately get that the determinant is 0. We'll actually prove this real quick in just a moment. It actually just comes directly from property 7. Property 9 also a really, really important one, so we'll star this. This tells us that the determinant of a product is the product of the determinants. So while you do not have that the determinant distributes over addition, so this is not true, right here, this is how the determinant does distribute. If you have the product of two matrices, then the determinant of the product is the product of their determinants. This one is very important. Later on, when we're proving some interesting results about like the determinant of an orthogonal matrix, we'll make use of this result here. And then finally, property 10 says that if A is invertible, so if you have an invertible matrix, then the determinant of its inverse is 1 over the determinant of the original matrix. This property 10, you should try proving on your own directly from property 9. Use A inverse is equal to the identity matrix. That's the definition of the inverse. Apply the determinant on both sides, and then go ahead and solve for the determinant of A inverse. And you should be able to derive this result. So this property 10 comes right from property 9. So I'm also going to star this one because this is definitely an important one. Notice that this one does have a condition, though. It says that if A is invertible. If A is not invertible, then obviously talking about the determinant of its inverse is nonsense, because you have to even have an inverse, you have to be invertible. Notice it also wouldn't make sense because if you're non-invertible, your determinant is 0, and you'd have a 1 divided by 0. Okay, so we're going to quickly go over proofs of a couple of these properties, mainly so that we can go back and prove property 3, which said that if you use that third type of elementary row operation, adding one multiple of one row to a different row, then the determinant does not change. So I would like to prove this for you because I promised it from the last one. So we do need to prove a couple of these other ones to get to this. Okay, so which properties are we going to prove? Well, we're going to try to prove 6, 7, 8, and 3. So we're going to go ahead and we're going to start by proving 6, which again, like I said, it's not that useful computationally. I mean, in certain weird situations like this, maybe, but to be honest, we mostly prove property 6 so that we can prove property 7 and property 8, and then we can pop back and prove property 3. So let's go ahead and prove P6. So for P6, we're going to so we're going to assume matrix A has the same rows as BC except in row R. We're going to assume that the rth row of A is the sum of the rth rows of B and C. And we need to show that the determinant of A is equal to the determinant of B plus the determinant of C. So how are we going to do this? Well, we're basically just going to translate this statement into a statement about the elements. So what we're going to do is we're going to say that the Aij element so the ijth element of matrix A is going to be equivalent to Aij for I not equal to that row R, and then Bij plus Cij for I equal to R. And we're going to make a note that for I not equal to R, Aij equals Bij equals Cij. So if we're in any row other than the rth row, the elements are identical. And if we're in that rth row, then for A, it's sum of the rows from B and C. Okay, so let's go ahead and then talk about the determinant of A. So the determinant of A is going to be that sum over the n factorial different permutations, the sign of each permutation times A1P1 times A ... so A1P1 down to ANPN. As always, we're going to expand this to include the sort of moment that's going to be interesting to us, which is going to be in that rth row. So the determinant of A is really the sum over those n factorial permutations. P1 down to PR down to Pn, A1 P1 down to AR PR down to AN Pn. Okay, now since we're talking about the rth row of A, we know that the rth row of A is the same as the sum of the rth rows of B and C. So the determinant of A then is the sum over the n factorial different permutations, P1 down to PR down to Pn, A1 P1, and we're going to now, I guess our notation here was always to circle what we're sort of changing because these can get pretty messy, and we're going to replace that with BR PR plus CR PR. Notice that we don't know what column we're in, that's why we have that P sub R, but we know we're in the rth row, which is why we can replace it here. And then, of course, we're going to go ahead down to ANPN. Now, this is a product. I mean, this is just a +1 or -1. So it is just a product of this, 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 onto these. So we can actually do this as two separate products. So we can say that this is the determinant of A is the sum over the n factorial permutations. So in other words, I'm going to distribute everything here and everything here onto there, and then everything here and everything here onto here. So in other words, just splitting this up instead of, so we actually have the sum of two separate things. So P1 down to PR down to Pn, A1 P1 dot 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 BR PR dot 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 AN Pn, and then plus the sign P1 through PR through Pn, A1 P1 dot 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 CR PR dot 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 ANPN. Now, as you can imagine, we have the sum of these sums, so we can split that up as two separate summations. So we have the determinant of A is the sum over the n factorial different permutations, the sign of the permutation, A1 P1 dot 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 BR PR ANPN, and then plus the next sum, which is the sum, again, over the same n factorial permutations, P1 down to PR to Pn, A1 P1 down to CR PR down to ANPN. Okay, we're almost done. The last trick is to remember that these, in every other row, every other row of matrix A is the same as every row of matrix B. It's the same as every row of matrix C, except for that rth row. So I'm going to replace all of these with B, so the corresponding elements from B, and I'm going to replace all of these with the corresponding elements from C. So I can rewrite this and say that the determinant of A is the sum over the n factorial different permutations, the sign of P1 to PR to Pn. We're going to call this B1 P1 down to BR PR down to BN Pn, and then plus the sum over these n factorial permutations, P1 through PR through Pn. Now I'm just going to call these C, so C1 P1 down to CR PR down to CN Pn. And then what do we notice? Well, this entire summation, that's the definition of the determinant of B, and this is the definition of the determinant of C. So we can say that this whole thing here is the determinant of B, this is the determinant of C. So as a final sort of result, we get that the determinant of A is the determinant of B plus the determinant of C. And there we go. We established our result. So the main thing here is it's sort of lengthy, not to say much, but all we really did is we sort of said, okay, every row of matrix A is equivalent to every row of matrix B is equivalent to every row of matrix C, except for that rth row. Now that rth row of A was the sum of the rth rows of matrix B and matrix C. So we focused on that one element, split it up, then said that everything was just being multiplied onto that sum, so we could do it as two separate sums. Then, of course, we were summing up those products, so we split that as two separate summations, and then we recognized one summation as the determinant B, the other summation as the determinant C, and we were all done. Now the other properties will run really fast from here. So let's go ahead and move on to the other ones. So P7 says if matrix A has 0 row / 0 column, determinant of A is equal to 0. Your textbook proves this by basically making the argument that the definition of the determinant always picks out one value from each row in each column in the product. So if there's a 0 row or 0 column, there's always going to be a 0 in every product, and the determinant's going to be 0. I think that's a totally fine proof, but I'm just going to give a slightly sort of more elegant one, I think, because it's going to avoid the need for making the argument about all those products of zeros. Instead, all we're going to say is that if matrix A has a 0 row, 0 column, then A, it cannot be row equivalent to the identity matrix. If you have a 0 row or 0 column, no matter what you do, you're always going to have that 0 row or 0 column, because as you do the different row operations, it's always going to sort of remain there. So that means that A cannot be row equivalent to the identity. So that means A is not invertible. So that means determinant of A must be equal to 0. Okay, that's nice and easy. Now we can look at property 8. Property 8 says that if matrix A has two rows that are scalar, 2 rows / 2 columns that are scalar multiples, then determinant of A equals 0. So that was property 8, right? Property 8 says if you have 2 rows or 2 columns that are scalar multiples of one another, then the determinant is automatically 0. So this one, I'm just going to prove for the case for rows. To prove the case for columns, you would just use the argument I'm about to use on the transpose and then use property 5. But for now, I'm just going to go ahead and assume we have 2 rows that are multiples. Assume matrix A has 2 rows that are multiples. Then we could use an elementary row operation to create a 0 row, right? If you have 2 rows that are multiples of one another, then you could use an elementary row operation to create a 0 row. So that automatically means that your determinant is going to be equal to 0. So the determinant of A must be equal to 0. So there we go. All right, what we'd like to sort of wrap up with, though, is actually proving property 3, which is the main one that we wanted to sort of talk about. So let's go ahead and talk about property 3. So we'll do that on one more sort of new page. So for property 3, we actually want to prove, we wanted to say that if B is constructed from A by adding a multiple of one row to another, then determinant of B is equal to determinant of A. Okay, so let's go ahead and assume matrix B is constructed by adding K times row R to row T. Okay, so what does that tell us? That tells us, well, that Bij is the same as Aij, except when we're in that teeth row. In the teeth row, we actually have, when I is equal to t, we actually have a, let's back that up real quick. So when you're in that teeth row, you have the original thing, ATJ, but then you get K times that row R, so you get times ARJ, and that's what happens at I equals T. So, in other words, we're saying that if you use that elementary row operation of the third type, what happens is that every other row stays the same, but in that teeth row, where you added K times row R, you have what was originally there plus K times the elements from that rth row. Okay, so let's look at the determinant of B. We'll be able to do this a bit faster here. It's going to be very similar to the proof we did back here for this guy right here. So let's go ahead. So here we know that this is going to be over the n factorial different permutations, the sine of p1 down to pn, and then our b1 p1 down to bn pn. Okay, but we can do a little bit here. We can say, okay, since we know that all the rows are the same except for this one, we could actually split this in sort of the way that we did in that proof of the previous property, in the proof of property, what was this number? Property 6 here. So we can sort of get right to this moment. So I'm going to actually skip writing this stuff out because we know that once we get this sum here, we can split it as the two sums here. So in this case, we can sort of get that this is the determinant of B is the sum over the n factorial different permutations, the sine of each permutation, and then we can say that this is going to go b1 p1 down to that one moment where we actually have that non-standard element. So let's actually just go ahead and replace all the elements. So we can say a1 p1 down to that moment, atj plus karj, and then down to the last one, which will be back to just being like the elements of A, so an pn. Then we can split that, like we said, we can distribute everything onto one piece and then distribute it onto the other and split it up as two separate pieces. So this is going to be the sum a1 p1 down to atj down to an pn plus the sum n factorial p1 through pn a1 p1 karj an pn. Okay, now it should be pretty clear that this one here, while this just has all the normal A things, this is just going to equal the determinant of A. But what about this one? Well, this might look like, well, maybe we pull the K out and we get something here. But remember, this right here, this tells us that this matrix has in its teeth position right here in the teeth row, it has a multiple of the rth row. So instead of having the actual teeth row of A, it has the multiple of the rth row. So in other words, this is a matrix whose teeth row is just a multiple of its rth row. And we proved right here that if a matrix has two rows that are scalar multiples, then the determinant is 0. So that tells us that this whole thing must have a determinant of 0. So this whole thing here is just going to be plus 0, because this is the determinant of a matrix who has a row that is a scalar multiple of another row. So this shows us that the determinant of B is equal to the determinant of A, which is what we wanted to show. So I know I went a little sort of fast here because this one is very, very similar to what we did back on property 6 here. But really, I hope you can see that once you have property 6 and you have property 8, those two together basically guarantee us that this property 3, which is the one we really wanted to make sure we had a proof of because it was the last elementary row operation, well, now we know that that really doesn't change the determinant as proven here. Okay, so let's go ahead and wrap up this video then, and wrap up this section about the properties of the determinants by just looking at a couple of computational examples, making sure we're sort of comfortable using and manipulating determinants using these properties. So in this first one that I'd like to do, we're going to sort of do this a little abstractly. We're going to, instead of trying to calculate more determinants of matrices, which we've done a lot of, we're going to just assume that we have these three matrices, A, B, and C, that are all 5 by 5 matrices. And we have some information. We know the determinant of A is 3, the determinant of B is -2, and the determinant of C is 4. Notice that tells us that A, B, and C are all invertible matrices because none of these determinants are 0. What we're going to do is we're going to calculate the determinant of some other matrices based on our properties. So the first thing we're going to do is we're going to try to calculate the determinant of 2 times the matrix A. So we said, how do you deal with a scalar? Well, this isn't a scalar being multiplied onto a single row. It's a scalar being multiplied onto all the rows of A. So by property 4, I believe that we would say, this would be 2 to the number of rows, and we had 5 rows, so it'd be 2 to the 5th times the determinant of A. Because this 2 is going to hit onto all the rows of A. There are 5 rows of A, so we get 5 iterations of that second elementary row operation. So we get 2 to the 5th times the determinant of A, which is going to be 32, and then times 3, because we know that the determinant of A is 3, and that's going to be 96 there. So the determinant of 2A must be 96. All right, for B, we have the determinant of AB transpose. How are we going to deal with this? Well, first thing we know is that the determinant does distribute over products. So we know that this is the same as the determinant of A times the determinant of B transpose. We also said property 5 on the previous list was that the determinant of the transpose is the same as the determinant of the original matrix. So we get determinant A times determinant B. And then, of course, that is just 3 times -2, which is -6. All right, then we have C here, the determinant of the negative of B inverse. First thing is, let's pull that negative sign out. B inverse, of course, we don't know what B inverse is, but it's going to be a 5 by 5 matrix. So this is going to be -1 to the 5th times the determinant of B inverse. How do I know B inverse exists? Well, because the determinant of B is non-zero, so it has to have an inverse. We said by property 10 on the previous page that the determinant of the inverse is 1 over the determinant of the original matrix. So this is going to be -1 to the 5th, 1 over the determinant of B, which looks like, since the determinant of B is -2, we're going to get -1 over -2, which is going to be 1/2. So we know, even without knowing what the matrix B is, we know that the determinant of the negative of its inverse has to be 1/2. All right, finally, this huge jumble, we want to take the determinant of A times the inverse of B transpose C inverse. So let's try to break this down piece by piece. We can first view this as A times this whole mess, and we know the determinant distributes there. So we can say that this is determinant of A, and then determinant of B transpose C inverse. And then if we wanted to, we could say, okay, the determinant of this inverse here is going to be 1 over the determinant of the original. So I guess we could say that that's determinant of A, 1 over the determinant of B transpose C inverse. And then, of course, this is a product, so we can split up that determinant. So this is the determinant of A, 1 over the determinant of B transpose, determinant of C inverse. And then, of course, we know that the determinant of B transpose is the determinant of B, and the determinant of C inverse is 1 over the determinant of C. So we got 1 determinant of A, 1 over determinant of B, 1 over determinant of C. Now we could just plug everything in. Determinant of A was 3, B was -2, and C was 4. So this would be 3 times 1 over -2 times 1/4, I believe. Yep, I plugged all that stuff in correctly. So this is going to be -1/2. 1 over -1/2 is going to be -2, and we should get -6 there. Okay, now this one's sort of interesting just because we did a lot of manipulations. Were there other ways to do this? Well, just as an alternate sort of way, I won't work all the way through it, but if you wanted to, instead of immediately putting the determinant, we could have actually simplified this. We know that the inverse reverses the order and inverts each piece. So we could have also said that we actually have the determinant of A, C inverse, inverse, B transpose, inverse. And then we could have said, okay, C inverse, inverse, that's actually the determinant of A, C, B transpose, inverse. And then we could have said, okay, let's sort of imagine grouping these two and this one separately. So that's going to be the determinant of AC and the determinant of B transpose inverse. Then, of course, now this is a product of 2, so we can split that up. We get the determinant of A, the determinant of C. Since we have this inverse here, we can make that 1 over the determinant of B transpose. And then we could say that's determinant A, determinant C, 1 over determinant B. Is that equivalent? I'm not going to plug in, but is that equivalent to this? Of course, right? Because this fraction here could flip up and we get the exact same thing. So a lot of different sort of paths to use here. You could have used some properties of the inverse and the transpose first, or if you wanted to do just all properties of the determinant, could have approached it like this. So why are we doing examples like this? Is this something that's super, important from a theoretical perspective? Well, not really. It's mostly here just to make sure you're comfortable understanding what the different properties actually said about the determinant. Let's do another example sort of similar to that. So we're going to again sort of do this from an abstract perspective. We have this crazy 4x4 matrix where we don't have anything except for letter names for all the elements, so A through P. We are going to assume that the determinant of this matrix is 3, and we're going to try to figure out the determinant of this crazy matrix. Again, by trying to think about the operations that might have been applied to go from A to B. Okay, so let's take a look at this. You'll notice that this thing has all these 2's attached to like I and J and K and L. Notice that that's a row here, and that's a column here. So it sounds like there's going to be some sort of transpose. Also sounds like we're going to need to multiply this by 2. There's also looking like there's some negatives. There looks like there's several things. So let's just start with sort of our modifications here. So if we do A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Well, let's go ahead and like we said here, we sort of notice that I, J, K, and L all have that 2. So let's go ahead and modify by taking 2 times row 3. And remember, the determinant here is determinant of A equals 3. So if I multiply row 3 by 2, I'm going to multiply that determinant by 2, and I will know that the matrix A, B, C, D, E, F, G, H, 2I, 2J, 2K, 2L, M, N, O, P. Well, that must have a determinant of 6. The determinant here equals 6, because I multiplied by a row by 2, so I must have 6 there. What else do I notice here? Well, at some point I'd like to do the transpose, but I might also notice that E, F, G, H all have negative signs, so probably a good idea to negate that row as well. So let's go ahead and negate row 2. So now we'd have the matrix A, B, C, D, negative E, negative F, negative G, and negative H, and then 2I, 2J, 2K, 2L, M, N, O, P. Since we multiplied a row by a negative, we know that the determinant of this matrix is now negative 6. Okay. Everything else is starting to look good. I guess if I start to think about doing the transpose of this, then my A, B, C, D is going to become my first column. That doesn't seem to work very well because I actually want it to be sort of the third. That might mean that I need to go ahead and interchange 2 of the rows. So let's go ahead and do that. So let's interchange R1 and R3. So now I have the matrix 2I, 2J, 2K, 2L, and then negative E, negative F, negative G, negative H. And then I have A, B, C, D, and then I have M, N, O, P. Okay, so let's go ahead then and actually perform the transpose now. Also, that interchange, of course, negates the determinant, so my determinant here is 6. So now let's go ahead and do the transpose. Notice that I wasn't writing row equivalences here because I knew at some point I was going to perform the transpose, which is not a row equivalence. I'm just keeping track of the determinant under each modification here. This is not a row equivalence because we're going to do some non-row equivalence operations, namely the transpose. So let's go ahead and take the transpose here. So now it looks like I would have 2i, 2j, 2k, 2l, negative e, negative f, negative g, negative h, a, b, c, d, and m, n, o, p. And of course, performing the transpose doesn't change the determinant. So if I look, things are looking pretty good. My top row looks good, and these rows look good. It's only this one that's a little off. I need to add this row to this one. Of course, we know that that's not going to modify anything, but let's just go ahead and write it out. So let's take row 2 and replace it with row 2 plus row 1, which means that we would get 2i minus e a m, 2j plus 2i, minus e minus f, b plus a, n plus m, 2k minus g, c, o, 2l minus h, dp. And because this is the third type of elementary row operation, we know that the determinant here would be 6. So we can conclude that the determinant of the matrix we were actually interested in, the determinant here, would be equal to 6, based on the fact that the determinant of this original unknown matrix was equal to 3. Again, this is more just to make sure that you sort of understand and can manipulate using the different properties for the determinant that we've established. All right, let's wrap up section 3.2 by proving a little result about those special orthogonal matrices that we mentioned back in 3.1. So, recall that an invertible square matrix is said to be orthogonal if its inverse is equivalent to its transpose. We're going to prove that if A is orthogonal, then its determinant is equal to plus or minus 1. Notice that the determinant is non-zero because orthogonal matrices, by definition, have an inverse. But we'd like to prove specifically, not only is it non-zero, but it must be plus or minus 1. So how are we going to do this? Well, as our actual proof here, A is orthogonal. So what does that mean? That means A inverse equals A transpose. We're trying to prove a result about the determinant, so let's apply the determinant on both sides, which we can do. If two matrices are equivalent, then their determinants must be equivalent. Is that true the opposite way? Can you say if the determinant of two matrices are equivalent, then the matrices are equal? No. Of course not, right? Because you could take like the determinant of the identity matrix is 1, and there are plenty of other matrices that also have a determinant of 1. Doesn't mean that the matrices are equal. So you can only do this way. You can say that if you have two matrices that are equal, then their determinants must be equal. Okay, now we can use some matrix, some determinant properties. Over here, we know that that is actually equivalent to 1 over the determinant of A. And the determinant of A transpose, well, we know that that's equivalent to the determinant of A. Now notice we could solve this. We can just bring this over. We get 1 equals the determinant of A squared. And then notice that if we have 1 equals the determinant of A squared, we can square root both sides and get that the determinant of A must be equal to plus or minus 1. Check. So if you have an orthogonal matrix, its determinant must be plus or minus 1. Does that mean that if the determinant is plus or minus 1, it's guaranteed to be orthogonal? Absolutely not, right? This is a one-directional proof. That's the only way that this statement is true. If it's orthogonal, then the determinant is guaranteed to be plus or minus 1. Alrighty, this wraps up section 3.2, which was all about the properties of the determinant. We've got one more section in chapter 3, namely section 3.3, which is basically a quick investigation into a computational trick called the cofactor expansion that allows us to calculate determinants in a slightly faster way. Some people really like the cofactor expansion way. Some people like the method we developed in 3.2, which was to use elementary row operations to get something into an upper triangular, lower triangular, or diagonal format and then use that theorem. But it is important to sort of see in a really sort of algorithmic approach to determining, to figuring out a determinant, and that's what we'll be doing in section 3.3.